Good afternoon, kids. Today we're going to look at states of matter. So we're going to go to physics section of the PhET simulations, and we're going to go into states of matter, the basics, right? Over here, you can see this is a container. It's a closed container in which we have solid gas. For our sake of work, we have neon, which is in atomic form. So these are atoms which are joined in together, bulked in together because the temperature is very low. If I put it in degrees Celsius, it's minus 259 degrees Celsius, and uh, the particles are very much close to together. And we do know that in solid, the particles are only able to vibrate around and collide them with, with one another. So they're, as you can see, they're colliding, and they're not going anywhere. They're retaining their shape because it's a solid. But if we had a liquid, as you can see, neon turns to liquid at minus 246. So some of the high energy particles that try to escape the surface. As you can see, the slowly particles going up, and over here you have a randomized motion of particles. Now they're not just vibrating anymore, they are moving about, but they're not able to move about freely in the container. Why? Because it's still a liquid, so liquid attains the shape of the container. And right now, since it's a cylinder, so it is settled all the way in the bottom. If I turn it into a gas, now you can see gas particles, they have free movement, and they do not interact much with one another other than the fact that they collide and they push each other apart. So this is what is happening. So this is gas. So I'm just going to start with water, right? And we know that water is liquid. Now these are water molecules. As you can see, these red and the white particles, they are attracted to one another. This is what we call as intermolecular forces, right? Or van der Waals forces, which is keeping water together, water molecules close to one another. And if we just cool it down a little bit and reduce the temperature, as you can see, let me just get to precisely 0, right? Yeah, at 0 and at 1. Now it is a liquid. As you can see, the particles are able to just move about, as well as evaporation is occurring, which is the escape of molecules of a liquid from its surface. If I heat it a little bit more, you can see evaporation is going to occur a lot more often. Particles will be pushed out the surface by the collisions, and these particles are now moving about at a much faster rate since the temperature is higher. And as I cool it down, their internal energy is dropping down, and hence they're moving slowly. And if I keep cooling it down, now it has become a solid. As you can see, the volume of the liquid was far less as compared to the volume of ice, right? If I keep cooling it down up to a point that there is no more movement left in the particles, as I try to get closer to uh, Kelvin, 0 kelvins, right, which is the absolute zero temperature, very close to it. Minus 273 is absolute, so I think it's minus 273. Yeah, this is now near to 1 Kelvin. Yeah, 1 Kelvin. It's not going to go any lower than this because 0 Kelvin is not achievable. 1 Kelvin is the last temperature that matter can achieve. So as you can see, no more movement. And as soon as I start heating it up, you see movement in the particles, which is the increase in the internal energy causing these particles to vibrate. If I keep on increasing, the particles are getting more and more energetic, up to a point that if I bring it to melting point, which is 0 degrees Celsius, let me get closer to it, 19 minus 10 minus 1. Now this is still in solid form, not purely liquid, since the particles are trying to retain their current positions even though they're moving very violently. If I increase the temperature, now it's melting. As you can see, some of these particles are moving, leaving their position. That shows that this is no more a solid but a liquid. And if I keep on increasing, it will become, it will turn into a gas, right? And we do know that water boils at 100 degrees Celsius. So at 100, the particles are nearly ready to escape the surface and become gas. As you can see, some of these particles, they are no longer being pulled down. Now let me just raise the temperature a little bit more. As you can see, At 150 degrees Celsius, water is now pretty much a gas, right? As you can see, these particles are no more interactive with one another. They're just colliding with one another and just moving about freely, just like gas molecules, right? So these are the three states of matter, and this is how they actually turn from one to the other, right? For so for solids, just vibrations. For liquid, you will see that the particles are able to escape from their current position and move to a new location. In gas, well, they're entirely moving freely in all of the area, right? Now you can have the phase changes, but we're going to go into the advanced version of this simulator as well, right? To just experiment with these thoughts. And over here we have a pressurized container. We can increase the pressure of the container by moving the slider down, right? Since we do not have a gas which can be compressed, solids and liquids, they are not compressible, right? If I try to press this down with a liquid or a solid, definitely the simulator is going to break off, right? I mean, let me just show that to you. uh, it will increase the pressure, and oh, there it goes. So I'm just going to reset this. I mean, it exploded because the pressure was so high, it could not retain the gas within this container. So I'm going to start with oxygen molecules, right? I'm going to heat it up a little bit so that it becomes at least a gas, right? So as you can see, if I increase the temperature, you can see the phase diagram in which it's moving towards gas. It's turning into a gas, right? It will turn into a liquid soon enough. You'll see once it settles at the bottom. Now, yeah, here you go. Now this is liquid oxygen, which is coming, settling at the bottom. If I leave the temperature here, now it has turned into a gas since the pressure is increasing. Now I'm going to increase the pressure. As you can see, as soon as I increase the pressure, the collisions are getting more violent, hence the energy of the particles is increasing, causing the temperature to rise as well. So increase in pressure causes an increase in temperature, and if I reduce the pressure, you can see the temperature is also going down dramatically. You can see this red thermometer as well as this pressure gauge is telling you this. Now let me just increase the quantity of the gas, and I will pump more oxygen particles in there. Let's see what happens, right? I'm pumping a lot of oxygen in here. Now you need to understand that oxygen helps in burning, so it is kind of a hazardous gas. If brought closer to any uh, fuel, gas or anything that can catch fire, it would make that uh, flame go violent. So increasing the pressure increases the temperature. As you can see, the temperature is going searingly high. I'm just trying not to, oh, it got overloaded. Okay, let's try again. I'm going to try and compress this before it all overloads and get back. Okay. Nonetheless, it's just a fun way to experiment with gases and liquids. Let's say if you have water molecules, if I compress water molecules, then it goes into this gas and hypergas state, which we don't want. And if I just cool it down, oh, it was 1,000 degrees. Okay, let's bring it down, bring it down. As you can see, as soon as I'm cooling it down, the pressure is also coming down. So over here we can see a direct correlationship between the temperature and the pressure. If the volume is not touched, this slider lets you decrease. Right now I'm decreasing the volume or increase the volume, right? So volume, if the gas is not increased, I mean if there's a fixed amount of gas in the container, let's say for oxygen, and the pressure is detectable, and if the temperature is not changed, increasing the volume or decreasing the volume is affecting both the pressure and the temperature to rise, right? So decrease in volume is directly inversely proportional to the temperature as well as the pressure. Now if I take temperature into account, then the change in temperature is actually directly proportional to changes in pressure, right? If I reduce the temperature, the pressure is also coming down, right? So it's a fun simulator. Just play around with this tool which is available. Keep your book with you. Have a look at the book, what the book is telling you. Try to experiment that over here in this tool, and you're going to have a very good time learning from the book as well as the simulator. I hope uh, some of these things that I discussed regarding the states of matter and the internal energy, the effects of the temperature and pressure, I hope you are clear. If not, please leave your queries in the question or in the comment section. I'll be able to, I'll try to respond as soon as possible. Thank you.